First is, or I'm using this notation 3. First step is initialization. Okay, uh, needs only one initial value. Let's look at how does it search. How does it pick the next value to try out? Okay, so that will be motivated by uh, this curve. Let me just draw a temporary curve, which is my f of x. Let me just draw, make life easy. Draw a curve like this. Okay, so let's say that this is my initial guess. Okay, so what Newton-Raphson method does is it basically draws a line, straight line, which is a tangent to the curve at x1. This is tangent. So this point, as you know, is x1 comma f of x1. So you drew a tangent, and uh, this point is where the tangent intersects the x-axis. So the coordinate, the y-coordinate of this point is going to be 0. Just draw it here. And it says that x2 is the best guess for the next iteration. Now, if that red curve was a straight line, the next two would actually be the answer, right? But since it's a curve and not a straight line, your new guess is not equal to 0. F of x2 is right there. It's not 0. So now with x2 as the new x1, you draw the next tangent and just keep repeating that till it finally converges to the value intended. I need to write a formula for how x2 is computed. So equation of a straight line is, so the straight line passes through x1, f of x1. So the equation of the tangent is, we know 2 points on the tangent. One of the point is this one, and the other point is this one, right? 2 points. So if you know 2 points, we can get the slope of the line. The slope of the line is f of x1, the y coordinate, minus y coordinate of the second point. Similarly, it's going to be the x coordinate of the first point minus the x coordinate of the second point. Okay, but the slope of a line or slope of the curve at the point x1 is nothing but the rate of change of the, the equation f of x at x1. So that's the derivative, first derivative. Okay, so solving for x2 gives us x2 equals x1 minus f of x1 divided by f prime x1. Okay, so that gives you x2. And then once you get x2, you repeat the process the same equation and get the new guess, like maybe call it x3. Then x3 will be x2 minus f of x2 divided by f prime x. Okay, so do you anticipate any problems with this method from that equation? Will we always be able to find an x2? Oh, it's super fast. This is like a magnitude faster, as you'll see. I'm not getting into the details on how to compute the convergence, but it's very fast. It'll take less iterations, much less than what we've seen. So we'll do the same example again. So what's the problem with this method? Zero, yeah. If the slope is zero, yeah, if the slope is zero, then you're in trouble because then you cannot find the equation. Okay, okay, let's answer that question, and just not with a proof, but just using the same problem. Let's take the same problem as we've taken before. Exactly the same problem, but we'll solve it with Newton-Raphson. And I think that I post the solution. I'm just trying to see if I posted. Yeah. So this was how fast the bisection method converged. It took 12 iterations to get 3 places of accuracy. Let's see how Newton-Raphson does compared to this. Here's a problem. Use Newton-Raphson method compute the root of the equation f of x equals x squared minus 3x. Use an initial guess of 4. Note that bisection we had to bracket the root, and I had given, I think, 1 and 4 was the bracket root. So we can try 1 and 4. I just tried 4, but you can also try 1. And the termination is terminate the search when the accuracy is 1e negative 3. Okay, so remember what we need. We need f of x, which is given to us. And then we also need the first derivative of x, that is derivative of x squared minus 3x is 2x minus 3. Okay, iteration 1. What we're trying to do is we're going to use x1 equals 4, and we want to compute f of x1. That's going to be 4 squared minus 3 times 4 is it 4? And then f prime x1 is 2 times 4 minus 3, 5. So x2 is x1 minus f of x1 x1 is 4, f of x1 is 4 divided by 5, 3.2. Okay. Every time we complete an iteration, we ask the question, are we ready to terminate? Well, if you compute f of x2, we see that that is 3.2 square minus 3 times 3.2 comes out to be 0.64. Okay, we see that that is much greater than 1e negative 3. So we're not there to terminate the search. Iteration 2. So now x1 is a new, our old x2, which is 3.2. F of x1, we just computed that, which is same as x2 is 0.64. F prime of x1 is 2 times 3.2 minus 3, actually comes out to be 3.4. So our new guess for x2 is going to be x1 minus f of x1 divided by f prime x1. So that's 3.2 minus 0.64 divided by 3.4 comes out to be 3.011. And if you try to find what f of x2 is, it's x 3. 0.033, which is clearly greater than 1e negative 3. So we've not converged yet. Okay, let's go to iteration 3. Looks like we're close. 0.033 is not too far from 1e negative 3. Iteration 3. So our new x1 is x2, which is 3.011. We've already computed f of x1, which is the same as let's see, 3.011. That's not right. It's 0.033. And then f prime of x1, we need to compute that. It's 2 times 3.011 minus 3 was 3.022. Okay, so x2 is x1 minus f of x1 divided by f prime x1. (3.011 minus 0.033 divided by 3.022. So this gives x2 equals 3.000. Oh, it's almost 3. F of x2 will be 3.0008 square minus 3 times 3.00008 is 0.0002, which is less than 1e negative 3. And so we know that we have found the root. This indicates convergence So we have root is 3.00008. It took iterations in 3 iterations. Okay, so they gave us a solution in 3 iterations. We even have to resort to using a computer program. It's pretty fast, from 4 to 3 in 3 iterations.
So this the function that you gave us to replace that 3.
Okay, I had here. I'm going to comment out regular falsy and bisection. It's the same file which calls those functions. So now it's set only to use Newton-Raphson. And one thing which I need to do here is that's my function, but I've not programmed the derivative correctly. So the derivative of x squared minus 3x is 2x minus 3. And for this one, the way I've done it is I only need one guess. A doesn't matter. The B doesn't matter. So the B doesn't matter. So I gave 4, right? 4, tolerance 1 negative, 100 is the tolerance. So let's just run this. Okay. It's not simply printing the root. Maybe I've not made it print the root, or maybe I did. Yeah, so it's supposed to print the root and then give me Newton-Raphson iterations. It's here. There. So the approximate root is 3.00046. And I think the reason I got 008 is because you know I truncate my solutions, right? I take 4 decimal places, and so it basically used all the decimal places. That's why it gave a much better estimate than what I got. 3.008 is greater than 3.004, which is closer to 3.000. It said 2 iterations because I think I started with the first one I counted as 0 iterations. It's really 3 iterations that it took. I actually have that here. This is what was produced. Start with 4, and it's just basically giving me the progress. 1, 2, 3, 4, 3.2, 3.0. I'm missing the 4th one though. It's 3.008.